things that we are doing at NVIDIA. We're going to talk about new product for years. Probably many people in this room, and us included, have been really trying to make this work, right? To turn AI models into things that do useful work and can answer useful questions and make useful predictions about drug discovery, about life sciences, about biology. And I think it's reasonable to say that it feels like an inflection point has happened over the last months, maybe year or so. The pace of the number of models that are developed is certainly increasing, but also their capabilities, not just as independent models, but as systems that work together, that as reasoning systems, and some of the clarity that we have needed for a long time in understanding what's necessary to get us to the next level of this AI and biology revolution, I think are starting to become fairly clear. Not that we know all the answers yet by any means, but I think that they are starting to become clear. And so I want to tell, this is basically the first slide of the talk, and it's also the last slide of the talk with a couple of different changes on the slide, and you'll see why in a little bit once we get to the end of the session. The first thing that I think has been really clear over the last couple of years is that we are in a data-starved regime in this space, and so there are many people in other industries, and so we need to focus on that. We work on models. We're very good as a company we have a horizontal platform and a lot of incredibly smart people for building foundation models across our ecosystem, but specifically in biology. So what can we contribute to the entire world? Largely collaborating with partners in order to improve the state of the art of what's possible from a modeling standpoint, and I'm going to talk about that today. We build lots of libraries. Perhaps this is what we are best known for, and I'm going to talk about some new libraries that we're releasing here. We'll talk a little bit about some multimodal stuff as well as we're thinking through this. Describe that, but basically we have and all of these. I just want to call out the incredible work of our partners in basically everything I'm about to say. So. Data. In biology, unlike in LLMs, we have very spiky, disconnected data sets. Is work in synonymous mutations. So we use this, and our partners are using this, and we're collaborating around a number of different applications of this technology. That includes things like mRNA stability and, of course, vaccine design. And so this is a really fundamental effort for us. It has a variety of applications. I'm sorry the video is not playing automatically. I thought I fixed that last night, and apparently it didn't work. A variety of applications that we're working on. This is all open source and in our BioNeMo ecosystem, so you can just go grab it. We've been working with synthetic biology teams, vaccine design teams, mRNA therapeutic teams. Anyone who's working on codon optimization or protein expression has been a great partner of ours, and this is also work that has involved a number of partners which we published on previously. So really cool work coming out of our bioresearch teams. We are also full steam ahead on making sure that we can actually generate and process all of this data that the world is building. And so Parabricks, I'm sure most people in the audience are aware of. We're now well into an incredible maturity, and it's just accelerating from where it is. Amazing work from the team. We've released a Parabricks 4.7 here at GTC this year. It has a number of specific new features, including a new pangenome germline pipeline. So you see new giraffe there, and small model support for deep variant, in addition to optimizations for Blackwell and future architectures that continue to scale this platform for genomic processing. And then we make all of these things available as end. And make it so the AlphaFold database was generated around that time. It has about 200 million monomers, and that did leverage quite a lot of compute. Right, these were inference time workloads that included an MSA step, that included the modeling step, and included some post processing to generate a data set of that scale. Modeling step with any model, including AlphaFold, was there on the right. And so what we've worked on pretty relentlessly over the last year and a half, and some of these things you're all using if you're a partner of ours, are three things. Operations in released, or this week we released, and it will be at ICLR later this year. It's a huge campaign. We solved more than we need to enable them to work on or working directly with us. Dyno released a new model this morning, which is noteworthy in this space, that combines some of the things that we did in Protina Complexa with what they're really good at. I believe the paper's out now, so you should go look, but certainly the announcements are out this morning. So this is exactly what we hope happens, right? Our goal is metadata. X-axis is a number of GPUs, and there's a reason that those are all squares, and I'll tell you about it in a second. And then the sequence length that you can achieve by scaling to number of GPUs, both in terms of memory and then obviously in terms of compute complexity as well, sharding in these types of tools. But we've been able to scale this now up to, I think 32,000 is the largest system that we've done, 30,000 amino acids on 64 GPUs. And in principle, there is no ceiling. We can continue to scale this out to infinity and address. But we've been able to scale this now up to, I think 32,000 is the largest system that we've done, 30,000 amino acids on 64 GPUs. And in principle, there is no ceiling. We can continue to scale. Regime there, actually, I had to look at my notes for a second, is in QSP, quantitative systems pharmacology. Think of these as things, if you're not familiar with this, it's hard to make those measurements. There are a number of different ways, though, that NVIDIA accelerated computing can impact downstream clinical workflows that are critical to service to generate therefore right now. And it's just a really awesome work, and takes advantage of systems. Lots more content. Stay in this room for the next talk. It's going to be awesome.
Grid. It's a geographically distributed infrastructure. Have excess power to put how AI grid improves the quality of experience for these use cases and regulatory compliances and telcos are the quality of better quality of experience are low latency. The concurrency queuing latency go hand in hand. A higher concurrency may get queued in a centralized set of hardware, and how we are distributing the inference points. And the bandwidth efficiency, like we talked about media and those use cases. For example, upon the reference or design, right on the acronym there. Cool. Okay.
Names on here that I want to point out. Professor Ozaki, everybody's, of course, Ozaki. There's two names on here. A bit of a shout out into doing dense linear algebra, and both with Ozaki 1 and Ozaki 2 methods, we can see great performance on these newer GPU architectures. So a bit of a shout out to the people that actually implemented these methods. Professor Ozaki, there's two names on here that I want to point out. Professor Ozaki, everybody's, of course, heard about. Ryo Yokota is actually at the conference too. I don't know if he's at my talk, but I met him yesterday, so he's attending GTC. But he's contributed in this area, collaborating with Professor Ozaki, along with Chino and Imomura Sensei. So another thing I'd like to highlight and do a plug is that Professor Ozaki will be presenting himself today virtually at 5 p.m. If you can't make it, of course, you can watch the recording later. But if you want to hear from him directly on how he explains the method works and what he's doing of late, then you can tune in and look at his talk. Okay, we're all looking forward to that. That's later this evening. Okay, so I'm not going to go into the details of how it works because he's done it. We've done it. He's going to do it again today. So there isn't a ton of value there. What we've been able to contribute in this area is actually how to productize this in a safe manner. So during the introduction, you heard I'm responsible for math libraries at NVIDIA. One thing we can't afford to do is ship math libraries that give wrong answers. So how do I productize the Ozaki method without anybody cutting themselves, right? I can't just ship it out there and hope that people use it correctly. So we wrote this paper and it was presented at, it's at the ACM website. Now it was presented at SC Asia, and all the algorithms and details are in there. You're welcome to take the QR code, but if you just search for guaranteed DGEM, the paper will show up. We developed a framework called automatic dynamic precision. This are moduli we need. I encourage you to read the papers to know, along with currently an opt-in feature, but our plan is to make this an opt-out. We know we can give the correct answers. If I sound a little bullish on that, when we started this journey a few years ago, we talked to James Demel from Berkeley, many of you know, and he told us he knows how to break the scheme. We said, please tell us how to break it. And future releases will keep, and I'm not quoting certain multiplication of GPUs, mk by kn dimensions for a C matrix that's m by n. You usually do that in tiles. And for each tile, you're basically doing a long tiled vector dot product. And if you give me a budget of memory, I can just kind of do like a split K type algorithm where, depending on the number of slices I need and depending on the amount of memory I have, I can chunk it and then do those multiplications in chunks instead of all at once. We're trying to reserve all that memory all at once. And when we do that, we actually use. So the chart that you see here is what we call a heat map. You'll see a few heat maps in this talk. And another thing I want you to take away from this talk is that you've seen a ton of data, right? Don't have to remember it all. The slides will be published. But if you see some uplift in totality, currently, the implementation in Kublas is leveraging the Ozaki 1 method, but we have the Ozaki 2 method actively under development, and it will be released soon. So I updated my chart. I used to show a different version of this chart in previous talks, where the x dimension is just square matrices, right, in growing size, and the y dimension is teraflops. And the numbers will match the specs that I showed you earlier, so it won't be surprised it's preserved. Depending on how difficult shape that you'll see. If it says 1.0, it means it's not giving you a speed up over native, but that's natural for that size of matrix. So this is to show that we're not just looking at like a marketing square matrix multiply, because the real world applications don't actually multiply those matrices. We always look at heat maps and try to maximize performance on these as much as possible. So this is the Ozaki 2 method coming to Kublas later of how you create an algorithm that solves the problem of interest to you. And then we do various, he wants to discuss these. This is the Ozaki 2 method for mixed precision. So there's three pillars of mixed precision computing, the way I see it. And if anybody wants to discuss these, I'd be more than happy. So we talked about the hardware portion. You need the capability to do various precisions and computations. And then we have the algorithm side. So how do you put those ingredients together? That's kind of like the recipe of how you create an algorithm that solves the problem of interest to you. And then you need tools. This has been the biggest common feedback. We don't have tools to study how much precision we need. And I will show you a prototype tool that we've developed that we're planning to release hopefully sometime in the near future. That will allow you to study how much dynamic range and how much precision you need in various parts of your code. That will make it very easy for you to exploit mixed precision. Otherwise, right now, it's a bit of a trial and error study. So without going into detail, I'll show you two examples. One of them is solving a linear system of equations, ax equals b. This is a very simple to explain thing. There's a lot of stuff on the chart, but I'll explain the idea and then I'll show you what it does in terms of performance and power efficiency. If you're solving a linear system of equations iteratively, the best preconditioner for that would be the inverse of the matrix. The idea is, hey, let's use the low precision tensor cores to calculate the inverse. It's a great approximation to an inverse as a preconditioner, and then we converge very fast, which is the chart on the right. Just a few iterations and you get to FP64 accuracy. There's a paper on that with lots and lots of data for many kinds of on that with the chart on the right. Just a few iterations and you get to FP64. FP64 accuracy. There's a paper on that with lots and lots of data for many kinds of generated matrices. So if you search for, once you have the slides, you can find those. So what this does to performance is really interesting. These are all effective performance or effective efficiency measures. So if you just look at Blackwell on the left, we're looking at teraflops. So this is effective teraflops of solving AX equals B to FP64 accuracy. And you're seeing almost 9x speed up, right? And the other interesting thing to see is going from Volta to Blackwell, this trend is growing. Similarly, if you look at power efficiency, again, for effective FP64 level of efficiency, the gigaflops per watt number, you're seeing that grow as well in a similar fashion, not surprisingly. So these methods are fast. They were faster on Volta. They've gotten a lot faster and they're a lot more power efficient. You can carry the same idea to an eigensolver. This is more in like R&D stage, so a lot of the data I'm showing here are preliminary and all subject to change. But what if you could build a 3-level Jacobi eigensolver where you basically start casting your matrix, you have to scale it to half precision, do a Jacobi eigensolve, then you precondition that in FP32, which is matrix multiply heavy. Then you do an FP32 Jacobi eigensolver, block Jacobi, and then you precondition in FP64, which is matrix multiply heavy, and then you finalize in FP64 to get your eigenvalues and eigenvectors. So most of the flops, as you realize, have been moved to BLAS3 in multiple precisions, both with all the tick marks. It's using everything from int8 MMA because of the Ozaki scheme, all the way to FP64 MMA, where it's faster than the Ozaki because of all the tick marks. It's using everything from int8 MMA because of this symmetric eigensolver is the one on the right-hand side with all the tick marks. It's using everything from int8 MMA because of to productize inside our, that was that light. As a computational scientist, you're worried about like how much force deviation I'm seeing. If I make changes to my algorithm, my precisions, will my results change, right? I don't, with just 6 bits energy calculation performance growth. And we're exceeding the 150 teraflop jam peak because some of these are doing mixed precision and exceeding the actual bars, which is 31 bits. You can stay below the e to the minus 6 error in energy, but the exact number, we can't accuracy.
A100. Is this
Whenever possible.
business to use. And we pioneered this work with a prototype at the end of 2023 and a word that you're going to hear again and again in the next year is 10 years in the future, we can also do the same. That's the permanence. Awaken notions of security around things like the actions of an agent, its capability, its intent, its lineage, its emergent behavior. This is really the paradigm of security that we need to enter into, and it requires fine-grained controls, so that as you can get signals that something isn't quite right, then you can take action. For instance, you can route the information to a different tool or to a different processor or to a different model. And if all goes wrong, and truly you have no other possible recourse, well then you can take the ultimate form of enforcement, which is that you cut access from the agent to its brain. That's really the power of this solution here, to have the attestations and the proof to know that you're making the right decision. And then once you do, you have an attestation that is persistent. This is the most advanced form of cryptographic proof, and what that means, at runtime, we can validate this. 10 years in the future, we can also do the same. That's the permanence and the importance of that type of proof, to know that the agent did the correct work and that it followed the rules. That certificate then, that powerful certificate, can be syndicated across a fleet of agents, where other agents can consume the certificate and say, okay, I trust this agent and the next agent. And if you think about it, what's needed in the agentic era for optimization, it's not just about speed. What's even more important is trust. Because if I can trust another agent, then I can delegate to that agent. I can divide what has attested to something at startup. That, in a sense, doesn't really capture the full risk, right? Because agents have emergent behavior. So it's really too early to have all the guarantees addressed at that point. Observability to another agent. It can't be spoofed. It can't be tampered with. And it needs to be syndicated, as I mentioned, to others. So that method of trust, of overhead, that is taxing on the ultimate performance around observability and evaluation and guardrails. Jensen likes to refer to this as a flywheel model. So that is a real breakthrough in being able to create persistent attestations every time that the model is run. We then put that into the agent. So here, the NeMo agentic framework powerfully presents a set of APIs and all sorts of capabilities around observability and evaluation and guardrails. Jensen likes to refer to this as a flywheel. And throughout that flywheel, every single one of those pieces requires their own form of verification so that you know what is going on with the agent as it's been constructed and deployed. So we can take those attestations, anchor it onto a ID, and then when it's loaded onto the verifiable runtime, we have now proof of the fact that this is the agent, here's exactly how it was created, and importantly, we have a continuous form of trust to know this is what is running. And so it's that idea which is really at the heart of the intelligence certificate that we created, and it uses a variety of very advanced cryptographic techniques, including quantum-resistant cryptography, and it creates a series of those attestations around the verifiable lineage, attestations around how this agent is in compliance, and then you have this on-demand form of credentialing. When we got to finally work with NVIDIA closely on this, we then began to optimize so that we get these proofs running at speeds that had never been seen before. And what we're really proud to show was that when we loaded this on the Blackwell architecture, it was to a single certificate that certifies a web-based agent, key feature for Anthropic's creation of that first very risky types of agents in a solution of decision. Do we continue by giving access to the brain, to the model? If it meets those requirements, yes. Do we continue to give it access to tools? We need proof. Resources, same. That's that highest level of trust that is required, and that's the only way that an agent can pass through that gateway. To have the verifiability, the enforceability of those rules, with fine-grained controls and dynamic intelligence, this is really a powerful solution that allows us to finally have a way to let these very risky types of agents into our enterprise. So let's show you how this works. So in this demo, what I'm doing is I'm loading up OpenClaw, and the first thing I'm doing is I'm going to add now an agentic identity. This is directly linked to the RFC 9421, which has been put out by Cloudflare. So what does this mean? Your agent can now go on the internet. You're welcome. So from there, we can proceed to provide compliance. So we can say this agent has been certified with the following competence, so that we know, for instance, that there's a NIST RMF playbook that has been cleared, or the EU AI Act, which is important to our friends over at Sovereign AI. These are the things that an agent's going to need to prove that it has competence in. And again, it's not just what the agent says, it's how it proves it. So here we have in our governance studio a way of creating those attestations around how it's compliant, presenting the evidence of how it's compliant, all of that notarized, all of that in a certificate. And so with that authority now to operate, I can issue the cert, and I have the ability to specify the time of when it's been issued, and also the possibility of it to expire or to be revoked. The agent takes that certificate of all of its lineage, of all of its governance, and now it passes it through the gateway. But to do that, critically, we need to know that this is the agent that's actually running. And that's the real breakthrough that we've announced today with the verifiable runtime, is I can have an attestation to know this is the agent that is actually running on this processor. I have a stamp of its configuration, and now, and only now, when I send the packets, it can proceed through the gateway. Because I have proof that this is the certificate of its competence, of its identity, and the fact that this is actually who I'm communicating with. This is what's running. So in the gateway, if I look into it, you can see here now all the agents that have kind of come on the radar of the gateway. And I can look into seeing what types of requests that they're making. I can see the credentials that they're putting forward. If there's been incidents, I can see that as well. And what's great about this is that we use AI natively inside the gateway, so that in fact I can look at those certificates, for instance, and I can get a semantic understanding of it. It reads essentially all those cryptographic statements and then makes it something that any user could actually inspect and understand. That's the power of this type of hardened certificate, is that it actually has semantic compatibility and interoperability. So if we continue, we can now go and look at the scans, so that the gateway itself becomes an active participant to say, hey, is this agent safe? Let's look it through. In this case here, we found a problem with one of its skills. That's noted. And then we can set dynamically the rules that are existing in this gateway, so that I can establish what are the key features that I would want as a gateway in order to let this agent through. So a specific sandbox, maybe OPA-RIGO policies, understanding its intent, maybe the fact that it has a credit card that's valid, establishing things like the scan of its code. These are the kind of baseline levels of security that are going to be required for any sort of agent to pass through a gateway. But what's critical, as I mentioned, kind of the theme of the talk, what's the proof? And what we can do with the gateway is we can say, look, maybe in some, not just seeing what's out there, but you're the ability to create compliance-ready factories. And so that, we have direct integrations into the leading enterprise. The real protection that we want for these lobsters, this is the type of thing that you're going to actually need. And what you're actually going to want is an independent, intelligent control. And so think about what that will give you. It's on 5G, 6G, and beyond. This is really kind of the next step of all right, thanks.
The intent needs to do. So we and thank you, Jonathan, for the first slide, is that we have so much context. Guardrails tells us that something is not right. AI node, which means that agents are ours, NVIDIA.
In a lot of the different press releases, companies like Microsoft, for example, integration. So why do I talk about the software? These culture thrive. All right, I'm going to go through the vertical pieces, and then I want to talk about how we're also doing that soil piece to get the verifiable compute. So we know that a lot of there was a particular hyperscaler who turned around and lost a box of their chips, and it ended up in a country where it wasn't supposed to be. This allows us to go verifiably all the way down to the
Together, it can require complex orchestration, right? It's very hard to set that up, and it can require technical depth to get that done. Autonomous workers and the AI specialists execute tasks using a team of AI agents that are at their disposal. And finally, I alluded to this, but AI agents can be very, very technically challenging to set up. It often requires prompting, evaluations, lots of detailed metrics work. All right, so here I am in ServiceNow's platform. This is the AI Agent Studio within ServiceNow. It's where I can come and define and deploy AI agents across the enterprise. We have thousands of AI agents that are working today to deliver value for customers and for businesses. And you can see some examples here, right? We've got more specific task-driven traditional AI agents that customers have been able to utilize and find ROI and value for their businesses. As you can see, there's some about benefits enrollment retrieval, categorizing incidents, etc. A lot of these will also power what Mayuka showed you with specialists that are able to tackle jobs end to end. You can see their core capabilities. You can see a little bit more about what they're able to tackle the organization. And pretend for a second that I am a service desk manager. So I'm looking at Kathy's portal here. And Kathy is an IT service desk manager within a company, an organization. She is responsible for making sure that tickets get handled, cases are addressed in a really, really timely manner. She runs a team, she manages an organization, and she is tasked with making sure that cases are resolved. When we scroll down and we look at the performance of her team, however, we can see that over time, the case volume has been increasing. That's here, the backlog status. And the time to resolution has also been increasing as well. And suggests to Kathy that she might add this level 1 service desk AI click. Kathy can an average handling time. And you can see here on the third row that the level 1 service desk AI specialist has a ton of increased capacity, and that's why it's able to address tickets in so much faster, so much shorter time, right? Log in case something went wrong, workforce, and our vision for actually getting work done. We believe that the ServiceNow platform brings together these two components to really help enterprises be more effective and efficient. It's employee works, meeting employees where.
Well, I have a quiz. How many of you are
oversight? So with that, I'm going to hand it back to you to take us through.
Thank you, Julie.
For actually getting
solve problems for your employees. But there is something
to advertisement, which is partially revealing information and trying to hook us in on the search and kind of product search. Everything went behind the chat now. Now, what happened effectively a few months ago is that the interactions and biased interactions that we have. And so that's the kind of evolution that we're speed running through. Now, as I mentioned, to do that well, it needs to have persistent execution, it needs to have memory, it needs to have all those features to effectively enable you to use it long term. Now, there's also another aspect which usually not talked in AI world, and really kind of through the year they evolved really quickly, and then the OpenClaw kind of launched this evolution of effectively personal agents, and now there is ZeroClaw. It leverages a number of cryptographic primitives. It prevents data infiltration, exfiltration, and prompt injection. There's a number of credential management systems that are stored encrypted and have policies. There's key management and kind of a number of other things to ensure that you can actually trust it with your context, with your data, and with your actions of a product. But now the decisions your agents make are completely different, right? So you actually want to make sure that what you run is verifiably yours and verifiably private. And so that's something we launched with NearAI, our cloud, that is providing you. You want to make sure that there is this is where you would order and purchase and also still be backward compatible, where it needs, given all the memory it has about you, given all the context. Usually in work 90%, and I want this much, right? Some B200s for a training run for 8 hours. I need to move steel, 10,000 tons of steel from Vietnam to LA port, right? And I need all the logistics figured out under the hood. I want to code review this project feature, or I need to drive some conversions, do some marketing for the landing page, right? So effectively anything that you do kind of with other companies and with other people can be described as this intent, the outcome you desire, and then the constraints you have to achieve that, and effectively allows you to now use this in kind of context-free environment, which is where agents are being extremely successful. So how does this actually work? Well, so we call it intent framework, and so it has effectively 3 core steps. So first core step is matching, right? So this is critical because this is, in effect with matching engine parameters. And so if agent accepts it, you need legal teams to actually design this, contracts, redline this problem, and then we'll reward based on how successful they were at solving this problem. And so the payment went back to the requester of the job because the job wasn't done. So this is just to show you kind of this is fully automated, runs, so even later for the matching engine. So to give you an example how but it didn't actually in this and is effectively generating revenue from that model. And effectively now managing it through the market.
Off as an ECN, for example. So NASDAQ was one of the pioneers of early kind of electronic trading back in the day as a market. Now, algo of a best bid and a best offer, and those are things that if you trade today, you'll be familiar with what that is. And also introduce what it to be. So, because the early high-frequency trading firms actually made a killing from this. Those were, if you talk to people who used to work at these firms back in the day, those were the glory days of high-frequency trading. Those are the early days that these firms were making hundreds of millions of revenue. It was an amazing time. Market near Chicago. And so the peaks here in that left chart, it shows how quickly the participants responded. And you'll see that is 2010 to 2014. So by 2014, that reaction time. So in the theoretical world, if everyone's reacting to the speed of light already, right? I guess maybe to ask you guys kind of a dumb question. If everyone's already reacting at the speed of light, how can you have an edge? In a world where, let's say, everyone can already be fast theoretically. Well, the only way that you can have an edge now, coincidentally, what happened, right? So at the turn of the century, they drove that open source movement as well. So there's a big open source movement. They created a lot of tools for training on machine learning models more efficiently. So things like XGBoost, PyTorch, TensorFlow, et cetera, right? Those are tools that hopefully you're familiar with. Around the same time, actually, let's see, my second company, I mentioned that I had a company that was the subject of a Harvard Business School case study on high frequency trading. So I spent almost a decade building a base of possible predictors is enormous in this space. And so while in fintech, maybe to give you an example as well, like comparison, in fintech, which is kind of a sister industry of ours, if you had a credit scoring model, like way before AI was a thing, so we built that, or that with volatility. XTX being the newest player in this industry. So the other ones have been around for a little bit longer. Now, I guess the question is why is the edge in algo trading shifting from being, latency sensitive, from latency to ML? Like, why are we shifting over to, being as fast as possible, being smart? In a nutshell, machine learning is scalable, whereas being as fast as possible being smart. In a nutshell, machine learning is scalable, fastest in the world. Apps like Robinhood and recently Kalshi Polymarket. There's a lot of retail trading apps out there now. 15 years ago, retail trading appealed to a very niche audience. But today, you think about like, my uncle trades, my mom trades, like everyone trades. My little cousins trade. There are literally retail trading apps that target real trader in your mom's basement kind of stereotype. That's actually not just like this year, which is used to have teams of people that needed to do this, but now you can literally just plug us into Cloud Code. By the way, it makes fundraising very difficult for us. Secretive, but it is no secret. Extremely useful in this space, and so we do provide real-time data as well. Yeah.
But not for HFT, obviously, right? That's not for collocations. It's more for
Well, that's a good question. Sorry, no, I didn't.
Let's start with what happens at request time. So we leverage what we call the bidder. It's called inference of a model. They all leverage tabular datasets. So tabular datasets are users, for example, the events, visits, sales, instead of text. So there are really two words of machine learning and AI. The online world, you've all seen them in paper competition, for example. So we have a mix of categorical features, continuous features. We also have embeddings that are the output of the models that we call offline. There's a mix of features coming from publishers, from product, and user features. For user features, we usually do, for example, aggregations from timelines, counters, which form what we call the feature engineering pipeline. A typical dataset has hundreds of features and is from. So for several years, we have a training stack of sales, LLH uplift of more than 2% by just changing one model with the exact same dataset, backbone and head.
Actually, we using predictive models. For each campaign, the business logic, we have so in time by any team ever, because we already use this technology on other projects. So this is this input compute time and output a lot of things in order to overcome this out of the table. We will now in particular and this is also visible on the GPU utilization metrics. So as long as the batch size keeps increasing. So on the top right, obvious here that we absorb our use case. Tensors aggregating data of all requests. Then this payload is sent to a model instance to produce a result which is batched. And in the end, we need to scatter this batch into individual responses. The main issue is that on this chain, several operations are single-threaded. And in order to build this inference payload, you need to do a double loop over all the tensors and all the requests. So in a single-threaded process, it's obvious that if we have a large number of tensors, it will be really difficult to have something efficient. So what did we do? I just mentioned we probably had too many tensors, so we decided to reduce the number of tensors. In order to do this, so the simple way to do this was for us to, in the client, before building the request to individual tensors, this already brought, since on this model all the features are categorical, we just, on the client, we add a hashing step to hash float features and string features, converting them into integers so we can concatenate them with the integer features, natural integer features. So in this case, we only have one tensor with more data, but we have only one tensor to send to the tritensor. Just mention how we reduced the number of tensors. This brought a 25 uplift in itself. And it also, having a single tensor in our model, also allowed us to better vectorize operations in the preprocessing. Then I give you a whole package of efficient, but at some point we now Python.
Sales. Some needed.
We have been able to use TensorRT, but since this
It's a very your work enterprise learning the right listing or not. On accuracy, we are matching, or in this case slightly outperforming, but that's in the range of noise, matching basically frontier models while being roughly 2x faster and somewhere between 4 and 5x. Natural language event that can happen in the this is an agent that
the company, we have a lot of proof. I think I'd like to welcome you here.
Levels of abstraction.
families such as Jira, Confluence, JSM, and different useful robots. Here's reinforcement query rewrite model, which is based on Google's Gemma 3 4 billion base model. It samples a group of different rewrites for the same prompt, and it computes. So this is basically our GRPO model improved recall at 10 by 6%, and we observe similar gains on the hard queries dataset and clear your. We break down the work into several specialized modules. The agent has access to a suite of, we found a duplicate, and then there's evaluation. We use 360 in-domain tasks.